Welcome. Welcome to the Plasma Physics course of EPFL. My name is Paolo Ricci. I am professor in theoretical plasma physics here at EPFL, and today I would like to introduce the concept of kinetic description of a plasma. Throughout the first part of the course, we have studied how particles, charged particles, move in a given electric and magnetic fields. Today it's time to look at, consider a more self-consistent description of a plasma, taking into account that these charged particles move under the effect of electric and magnetic field that they have themselves generated. So, as a first step in today's lecture, we will start from self-consistent description of a plasma, the most complete description we can come up with. And then we will introduce the concept of distribution functions and giving some example. And then, starting from the fact that particles are conserved, we will derive an equation, the Boltzmann equation, which actually states how the particle distribution function evolves in time. The self-consistent description of a plasma starts by noticing that once we know the forces that act on each particle, we can note the position and velocity of all particles by using Newton's law. For all particles, from 1, 2, 3, till the last one, n. More precisely, what we want to do is to consider the mass times the acceleration equal to the forces that are acting on each particle. And this, as we are dealing with charged particle, electrically charged particle, will be given by Qi E of Ri T plus the Lorentz force Vi cross B, B evaluated Ri T. Once we know the position and the velocity of all particles, we can evaluate the charge density and the current density. In fact, the current density will be equal to the sum over all particles of their charge times a delta function that takes into account that particles are located at the position Ri. And therefore, the contribution of the charge will be equal to 0 everywhere else but at their own position. Similarly, for the current density, we will have that this will be equal to the sum over all particles, charge of all particles, times their velocity, times the delta function that takes into account that particles are located at Ri. Once we know the charge density, the current density, we can evaluate the electric and magnetic field. And this can be done by using Maxwell's equation, which states that the divergence of E is equal to rho over epsilon 0. The curl of E is equal to minus dB over dt. Divergence of B is equal to 0, and curl of B is equal to mu 0 J plus epsilon 0 dE over dt. Once we have evaluated the electric and magnetic field by solving Maxwell's equation, we can actually evaluate the force that acts on each particle. In fact, the force that acts on each particle will be given by the electric force with the electric field evaluated at Ri plus Lorentz force. The system of equation that I have just described actually is able to represent carefully, in the most complete way, the dynamics of the plasma. It's able to describe the evolution and motion of all the particles that constitute our system in the electric and magnetic field that are self-consistently generated by their presence. The description that we have given of a plasma, it's very complete, very accurate. However, it's not practical. It wants to describe the evolution of a huge number of particles. Just to give you an example, there are about 10 to 21 particles in a fusion experiment. It's way too many to deal both numerically and analytically. We need a different approach, a statistical approach. This is why we are going to introduce the distribution function, which is a function that tells us how particles are distributed, are located in phase space. Phase space, it's a 6-dimensional space, 3 dimensions in velocity, 3 dimensions in configuration space. It's something that I cannot represent on the screen, that here on the 2-dimensional screen, and therefore I will do a projection of the 6-dimensional plane on the 2-dimensional plane that we can look at. And here is the projection of the 6-dimensional plane for what concerns the configuration space position and for what concerns the velocity position. Particles are distributed in this phase space, and I will draw a few of them. They are these points that I am representing here. And well, let's consider a volume that is large from a microscopic point of view, so that there are many particles containing to it, but which is still small by looking at it macroscopically. This volume will have an extension that is given by dV along the v direction and dr along the r direction. Now what we do, we define a function, the distribution function, f, which is a function of position, velocity and time, such that when t value of this function is multiplied by dr dv, what we obtain is the number of particles at time t that are contained in the phase space volume dr dv, centered in r and v. Now actually there is a distribution function for each species, and therefore for each species we will have a distribution function that we will call fs. S is the index of the species that will depend, of course, on position v and t. Some interesting quantities. First, the total number of particles for species S, that we'll call it capital NS, and this will be the integral over all position, over all velocity of the distribution function. Another quantity of interest, the number density, which represent the density of particles independently in configuration space, independently of their distribution in velocity space. This will be a function of position and time, and will be given by the integral over all velocity of the distribution function. And finally, the average velocity, which is a function of position, and which is given by the average of the velocity of the particle of all particles, weighted according to their distribution function. We have introduced the concept of distribution function. Let's give some examples. We are going to consider distribution functions that are independent of the spatial coordinates. We will, in other words, consider a uniform plasma, and we will consider distribution functions that also do not depend on time. Probably the most known example of distribution function is the Maxwell-Boltzmann distribution function. This is the distribution function of the plasma particles once the thermal equilibrium is attained. It states that particles are distributed according to a Gaussian distribution function. If we specify this distribution function in one dimension, we have that f0 of v, this time is not the modulus, is really the one-dimensional distribution function, is equal to n0 of 1 over 2 pi v thermal, this time to the 1/2, exponential of minus v squared divided by 2 v thermal squared. We can draw this distribution function and this for the one-dimensional case as a function of the velocity. And what we have is a curve that peaks at v equal to 0. The spreading of this curve is given by v thermal. Another interesting function, distribution function, is a monoenergetic beam in one dimension. And this will be given by f0 of v, that is equal to n0, delta function v minus v0. v0 is the velocity of the beam. Basically, all particles have a velocity that is equal to v0, and there are no other particles that have a velocity different than v0. If we try to draw this function, well, it's very difficult to draw a Dirac distribution, but at least intuitively we can give an idea of how this distribution function looks like. And in fact, the distribution function will be equal to 0 except that v equal to v0, and will be something very close to 0. And then we're at around v equal to v0 will go up to infinity. Of course, I cannot go out from the screen. And then we'll fall back to 0. The last example of distribution function that I would like to give is two counter-streaming beams in one dimension. In that case, the distribution function is given by the sum of two Dirac functions, one centered at v0 and one centered at minus v0. For example, the distribution function in this case will be equal to 0 everywhere except at minus v0 and at plus v0. Therefore equal to 0 up to minus v0, where it will go up to infinity. Of course, here too I cannot represent that. Then go down back to 0 up to v equal to v0, where it will go up to infinity again, and then it will come back. Now that we have introduced the concept of distribution function and we have given a few examples of distribution function, we can start to derive an equation that shows how the distribution function evolves as a function of time. To do that, the starting point is observing that particles are not created nor destroyed in phase space. So the starting point of this equation will be the observation that the particles are conserved in phase space. Let's try to translate it into mathematical expressions. Okay, let's start from our phase space. The 6-dimensional phase space that here I have to project over 2 dimensions, and where the particles are located. If there are no sources nor sinks of particles, then if we look at a small volume present in our system, what we will observe is that the variation of the particles contained in this small volume will be due to the flux of particles inflowing or outflowing from this volume. In other words, it will be given by minus the divergence that has to be evaluated in a 6-dimensional space, in the 6-dimensional phase space of u, which is the velocity at which particles are moving in the phase space, times fs. This is something that tells us that particles are conserved. They are nor created nor destroyed. What do I mean with this nabla in 6 dimensions? Well, this is the generalization of the nabla operator that we know from the 3-dimensional space to extend it into velocity space. So this will be equal to d over dx, d over dy, d over dz, and then dvx, d over dvy, d over dvz, which is also equal, and we will shorten this as the nabla operator in configuration space that I will write as d over dr, and the nabla operator in velocity space that I will write as d over dv. Now u, what is u? Is the derivative of r with respect to time and of v with respect to time. And particles change their position in time, and this change is equal to the velocity, and they move, they change their velocity according to their acceleration, which is given by the force divided by the mass of the particles according to Newton's law. And this, in other terms, is equal to v. And then, well, the forces we have to divide in two. As we know from the first part of the course, there will be long-range force that will act on our system, plus short-range forces. The long-range forces are the forces due to collective effects that occur on not to a global evolution of our system, while the short-range forces are due to collision, basically one-to-one particle interaction. Just to be clear, LR will stand for long-range forces, the one due to collective effect, while with us SR we will denote short-range forces. Okay, if we introduce this expression into the continuity equation in the 6-dimensional space, what we obtain is that df s dt is equal to the part of the divergence that is the one in configuration space, so it's minus d over dr of v fs minus d over dv of the contribution of both long-range and short-range forces. Here we will have translated this 6-dimensional operator into an operator of real space and velocity space. The conservation law that we have just derived can be put in a, let's say, more usual form, the so-called Boltzmann equation, which is the equation that is can be used to describe how the particles, the distribution function evolves as a function of time. So the starting point is the conservation law that we have just written. Let's make a few observations. The first thing that we have to notice is that as V is independent of R, as V and R are independent phase space variable, then we will have that the divergence of V fs is equal to V dot dfs over dr. Second thing that we notice is that the forces that we have written are actually electric and magnetic forces. So F long range, for example, will be equal to the charge of the particles multiplied by the electric field, the long range electric field, plus the Lorentz force. Now, the electric field is independent of V. the Lorentz force is perpendicular to V. This implies that the divergence with respect to V of F long range Fs is equal to the force long range dot dFs over dV. What does it mean? Well, if we use this expression in the calculation, into the conservation law that we have written, we have that dFs dt will be equal to minus V dot dFs dr minus, let's separate the contribution of long range and short range forces. So it will be the long range forces dot dFs over dV minus the contribution of the short range forces. We can rewrite this in a more usual form by bringing these terms on the left hand side and leaving the short range forces on the right hand side. This term here is actually a term that is related to collisions. It gives the evolution of the distribution function due to collision. Is something that is usually then called the collision operator and is denoted as df over dt, put a small e paid c to say that this is due to collisions. From this we get an equation where I explicitly write the forces as the decomposition of the electric and magnetic force, which is known as the Boltzmann equation. So here we got to the end of today's lecture. What have we done? Well, we have approached the self-consistent description of a plasma by taking into account that particles move under the electric and magnetic field that they have themselves generated. And therefore what we have done was to introduce the tools to describe the system of many particles. We have introduced the concept of distribution function, and then we have derived, by starting from the conservation of particles, an equation, the Boltzmann equation, which states how this distribution function evolves in time in the phase space.